Violeta Vogel. I'm head of data science department at Insel, which is the biggest university hospital in Switzerland. I'm sharing my talk with my employee, Benjamin Ellenberger, who will be presenting later on his work, concrete use cases. I want to show you broad overview of what we are doing and who we are. My slides are in German. I hope that's okay for most of you. The team I'm leading contains 7 employees for now. We will be growing. I have some people who studied physics. I have employees who studied bioengineering. Benjamin, who will be talking later on, is studying computational science. We have some people who had made their PhDs in pharma. We have some computer scientists, also some people from the business. So very broad, very different skills, and all of them are also needed. And one thing what everyone has in my team is we all know data and we can work with data and we love data. What we do is there are 3 fields. One of for with the data, because there is a law in Switzerland, but also in all other countries, which strictly says what is allowed, what data is allowed to use and how it has to be used in order to make research in a medicine. So we are making sure that we give only the data allowed, and that we and that according to the law. The second part is data engineering. We work with medical data, and we do all the data engineering tasks you guys learn at the university. And Eric can tell this better than I do. So it's very important that for us. The data we use, we get from the data warehouse. So we don't care about the data in a different clinics. There is another department who brings the data into a data warehouse. We work with structured data, with unstructured data like text, and we also work with the pictures. You can imagine that at the hospital, the main data is in pictures or some text. But also, of course, machine data from the different machines, and also even handwriting notes from the doctors, which is a different topic to talk about. What we also do in a data science is we do kind of e-alarming. For example, for multiple sclerosis, we have an e-alarming system which connects with data which is being analyzed at the moment, and sends the results to our system, and so that the doctors who treat the patients with multiple sclerosis, they see whenever there are changes in a blood of the patient, so they can react at the moment and contact the patients. And this way we saved a lot of patients from getting blind or losing some of our senses. On the other hand, we support our doctors on the in administration work. You just can't imagine that the doctors have a lot of work to do besides the treating patients, and they have also a lot of work to do because they need to report certain cases to the governmental boards. So we support them there with our analysis and with our automated work. And another part, and this is what we will be talking about today, is analysis and probabilistics. So, and in this case, I give the word in this stage to Benjamin, who is a data scientist in my team. He's doing his PhD at the moment and working on the very interesting project. Benjamin, the stage is yours.
Okay. Hello, everyone. I hope you can hear me, and I'll try to share my screen swiftly such that you can see what I want to show you. This is my entire screen. That's good. See my screen being shared. So you can't see my screen because it swiftly showed me that I have to restart my computer or the PowerPoint. I think you can see my screen now, right?
Yeah, yes. Perfect. Thank you.
Perfect. So, okay. So welcome to my talk, and I named it Computational Methods to Mitigate a Multi-Drug Resistant Organism Outbreak at a Hospital. I am Benjamin. I'm a data scientist at Insel University Hospital at Bern. And I'm going to give you a talk that is probably not your average talk that you've heard until now or that you will hear today. So I'm trying to present here a very real world case where you have to deal with all the sorts of things that happen when you dive into real world data, which is really messy and which is really the way it usually happens in the world. The world is messy, and so we have to deal with this and we have to clean it up in order to make sense of it. And that is what I'm going to present to you here, because that's what we do. So the case I'm going to talk to you about today is basically the problem of multi-drug resistant organisms in hospitals. This is a general issue in many hospitals, which means that you have bacteria that are within hospitals, and these can generate some kind of resistance to things like antibiotics and such, and therefore they are much more resistant to all the treatment that we usually give patients in order to heal them from their diagnosed diseases. And this is not something that should happen usually, and that's exactly what we're trying to avoid. But there are situations where this is really difficult because there are people that have specific conditions that lead to problems when they are infected with such organisms. So the specific organism that I'm talking about today is the VRE. This is the vancomycin-resistant Enterococcus. We had a spread in our hospital in early 2018, and it is confirmed to have its origin in Australia. But this is something that just lives everywhere around us. And so it's not something that just happens specifically in Insel Hospital. It's something hospitals don't really want to talk about, but it's something that happens. In our case, it led to about 300 patients that have been confirmed positive for VRE. And these are also kind of carriers. This means they carry it for up to about 6 months. So it's not something that just goes away very, very quickly. But it has to be mentioned that this is something that is completely normal to every human. So we all have kind of VRE somewhere in our body. Actually not. We have Enterococcus in our body, but not the vancomycin resistant one. We have this in our colon. And this just lives there. And as long as it stays there, it doesn't do anything to you. And also, if you get VRE, actually, the colonization actually has no effect on you mostly, because about 98% of the patients have no issues at all with this. It just lives in your body, and at some point, within 6 to 18 months, it is replaced by other bacterial populations. And it is transmitted to through direct contact, meaning something like a handshake, and then you touch your face or your eye or something. This can actually transmit this. And it's also living on surfaces, which is something that a lot of people have been discussing also with COVID, which seems to be no longer true. And this is pretty good for this situation. In our situation, it's actually a pretty bad situation, because then you really have to clean a lot of surfaces. And this means we have a lot more situations than just like people coughing at each other or shaking hands. And so, yeah, VRE is only problematic, as I said, for people with certain conditions, which is usually the situation where they all are already vulnerable due to the treatment, such as immunosuppression in chemotherapy. And in order to get such a VRE infection away, you basically have to treat it with special antibiotics. And this is a huge issue as such, because if you usually use this vancomycin antibiotic, which is very common. So then you have these organisms that get these resistancies, and then you have to pay attention that they don't get any other resistancy, because then the Enterococcus gets more and more dangerous, because at some point you will not be able to get it away except for your immune system reacting to it. And immunosuppressed patients, they cannot do this, and therefore it's really, really dangerous to them. So why is VRE a problem in hospitals? Basically, a hospital is a hotspot for vulnerable patients. We don't treat completely healthy patients. Sometimes we do, maybe, but usually we don't. And also, a lot of contact points between patients, doctors, and nurses, and devices and rooms are always there within a hospital. So all these surfaces that I was talking about are actually there, and they are contaminated, and we have to deal with this in order to keep the hospital clean and the patients healthy. So what did we do to solve this until now? Or what did the hospital do prior to this outbreak? So this is something that they have to monitor on a daily basis. And what they did is basically they looked at all the movement data of all the patients within the hospital, and looked at and used a proximity-based approach, which means that they basically looked at patients within the last 7 days that are on the same ward. And then they checked whether they were together in a room or something for longer than a day. And then they tried to find out whether there was a VRE positive patient on the same ward or in the same room with a patient where the status is unknown. And these patients then are set onto a screening list, and the screening list is what when we screen people in order to find out whether they are VRE positive or not. And for this, there is some logic implemented in our SAP system, but this is really, really limiting, because it's very cumbersome to first of all get the data, which is usually you just get a huge Excel sheet full of interactions, and then you have to screen through them, and basically all the proper modeling happens in your head. You look at this, and you find in the list your VRE positive patient, and you check where they interacted, and then you're tracing this down like a detective. But that is all in your head and maybe on paper, and there was no system in place to really help this. And the scope is really limited also to a single ward. So basically, you cannot see what happens if the VRE positive patient is moved to another ward. Then you have to re-ask the same question: what happened on this ward? And so in this model, basically, there were just two types of nodes, which were the wards. Maybe we can also say there were the rooms, and there were different patients, but nothing more. The primary point of transmission is basically the patient-patient interaction. So when a patient sits in the same room with another patient. And this is very limiting because, as I just told you, the surfaces can actually be contaminated. People can actually carry this around without having symptoms. And this is way more, this has a much larger dynamic than what this status quo here is modeling. So what we thought about here is basically we try to model a new approach, which we call here VRE carriers, which is this situation which assumes that VRE is transmitted through surface contacts or carriers. And as such, we can have actually these kind of second order or higher order transmissions, meaning one patient meets a certain person, this person goes to another person, this person goes to another patient, and then this other patient is also positive. Check for different time windows of how contacts are distributed. So if we are looking at contacts over a very much longer time, or if it's just a very short time contact where one patient is met at one day and the other patient is met at a second day. And this considers all possible nodes that are currently monitored in our data warehouse, which are the patients, the wards, the rooms, the employees, and the treatment devices. For now, we found these as the main agents that move around within our hospitals. So rooms don't move, but they are basically moved towards one of the other agents. And that when they meet, there is a possibility of having a transmission of VRE, whether it is onto a patient or a person as such, or if it's onto a surface. And this would hopefully lead at some point to automatically identify the rooms, devices, employees, and the patients that are interacting in this situation and are subject to having such a transmission, and then we should be able to screen them. But we are also interested in looking into whether there are something we call VRE hotspots, which is a more general term of saying something that either is a super spreader, for instance, something that distributes this VRE a lot, or if there are some people that are highly vulnerable. And in the end, we would also like to understand more about VRE transmission, how we actually can contain such an outbreak, and how we can prevent future outbreaks. So. But first of all, this is when the real world actually hits pretty hard. Sometimes a fast approximate solution helps the most, and this is actually the status quo that they implemented first, because it's a very cheap situation, a very cheap measure. It takes some time, and it takes a lot of people to screen to screen patients and to play detective, basically. But it's pretty hard to just drop in a new system when you have a running outbreak at the time when you learn about it. And so at the time of the outbreak, we had a little chance to get an automated approach up and running. And from what we understood from their business is that it's a lot better now that we provide this data in a very fast manner and build a better overview. And this was really effective enough to support the containment of the outbreak at the time. So when you look at this picture here below, you can see that there was an increase of patients in over a number of weeks. And then at some point we had this point in time when we started the bundle of outbreak management measures that we introduced there, and you can see that we were successfully containing this outbreak, and in the end there was close to no one positive anymore, or we were closely monitoring them and isolating them, such that this would no longer happen. And how did we do this? if you look at all these different data sources, this is what you usually get when you are within a larger company. You have a lot of different source systems, and we, in our data warehouse, we started to collect different source systems and loaded them into our system, into our data warehouse. And then what you can probably see if you're familiar a bit with data loading and transformations, you see that there are a lot of tables called LA, which means they are landing area, which means they are actually still pretty messy. And this was exactly when we started working hard on our data warehouse when this outbreak happened. So we actually had to work with all these different types of problems with that you see in data. First of all, you have to even make sense of them, and you have to find out outliers, and you have to find issues in the data that are there because these are not modeled properly within the source systems. But we had to do it because we wanted to merge this data into one large data set. And if we go along this kind of network, we built a network basically of these interactions between the patients, the rooms, the devices, and the employees, in order to find out who interacts with whom. And if you look at this a typical appointment, this basically means how you have a certain patient here. It's P2, and he is interacting with a certain employee. He's placed in a room, and he's treated with a certain device. And in the same room, we also have a patient 1, which is not considered here specifically, but he is also in the same room, and because he's there, it's also an interaction that happens at the same time. And this is what you can see how we extract different information about these different nodes in order to have some ability to trace back different properties of them, such as for the patient, for instance, we have different surgery codes and the diagnosis and the VRE status, but also their case IDs, so what they're actually treated on. And from this, we can also get all this data about employees and devices. And if you look at different edges are basically the interactions here, and they are time dependent. So I mean, we are not meeting all at the same time as we are right now meeting here in this call. But usually let's say before COVID, people actually met in certain rooms, and they were actually face to face, and therefore this is a time dependent meeting usually. And when people then part again, this interaction is no longer there, and we have to account for that here in our network. And this is exactly what we did here. We were basically building this kind of situations where you can build something that we call snapshots, meaning we can actually look into these situations and then find out who has had an interaction with whom. So if we look at this kind of interaction here, we have these different date and times of interaction. And we could then basically produce these snapshots by saying we want to get the only patients within a certain time range. And then we could just basically cross out these interactions, cross out the not interacting nodes. And then we got some kind of snapshot. And this snapshot, for instance, would now tell us that there is one patient. If this patient is very positive, we have this device, this room, and this employee that is interacting with them, and possibly they are somehow contaminated and could be up for kind of a screening. If there was another patient in this that was, for instance, interacting at some other point later with this employee, that would be a first-hand screening target. And this then separates basically your full interaction network that is showing all interactions across all times into different networks at different points in time. So basically you have different, you can see that there are certain nodes that go through all of these networks, and in some situations you see that there is a certain interaction, and in some situations the interaction is not there. And then we could basically give this, allow the end user of the hospital anti-infection team, we could allow them to query this network for snapshots of time range and location, and this made the search much easier for screening. So, but is this all what we could do? No, we could do a lot more. We thought at least about a lot of different ideas how to deal with this situation, because there is an inherent issue that is going to come up in this talk, which is that there are, because we have a certain policy in place how we screen people, we never have the full ground truth. So we only have the screening information about people that we screen. And we don't screen the whole hospital at one point, because that would these costs would be very intense, because such a screening actually entails not just one screening, but it's about 3 screenings, and then 2 of them have to be positive, and then you have to either isolate this person already after the first or second one of positive ones, because you don't want it to spread. So you can see that if you did this for the whole hospital, and if there was just some uncertainty of any of these screenings, you would have a huge amount of people that you would have to isolate in single rooms, and that would be intense. But what we tried to do here is basically we looked into 2 approaches. One of them is graph theory, and the other one is a bit more machine learning approach, to find out if we are looking for the right screening targets here. So first of all, you might be familiar with graph theory, or you might not. And you might be familiar with graph centralities, but what you will have to take away from this slide is basically graph centralities are an approach to find important nodes within the network. And important has to be defined depending on what you want to find out. Here on the right, you can see different networks that connect different nodes. And you can see the different centralities that show different locations or different nodes as being important, being highlighted in red, for instance, here in this situation. So what this could be is, for instance, you have the degree centrality, which basically is in subplot D, and this could show you, for instance, who has the most first-order interactions with other people. Whereas, for instance, the eigenvector centrality in subplot C shows a much more specific question, which is basically who has first-order interactions with others that have also a lot of first-order interactions. So in recommendation systems, for instance, Google had its first prototype, which was called PageRank, and this was also in place for a pretty long time. And this was basically eigenvector centrality, which was basically just looking at websites that are already of some reputation. And if they mention your website as being a website that is specifically on a certain topic, then this website, you basically get also some reputation. So if some random page on the website, on the internet mentions you as being a specialist, that's not as much information about you being a specialist as if I don't know, the most important expert in the field tells you are the most important expert in this field. Then you are also probably a pretty good expert. And this is what graph centralities do. And we thought possibly they can also tell us a bit something about our situation and how the very positive patients transmit VRE to others. So we started to develop different of our own specialized graph centralities, because that's what you usually do. Mostly you can start with with the classical ones, and then you find out there are certain things that you have to look into a bit more specifically. In our situation, it's actually we want to only look at infected patients, and not just at all kind of interactions, because if patients interact, that's not such a problem as such. But if you interact with infected patients, then that is a problem. And so this is basically a degree centrality, but a bit more specifically on infected patients. And therefore, we looked at this ratio between infected patients versus the total patients. And this, as such, is basically a measure for a hotspot, because then you can get information about how prone a certain room, for instance, is to transmitting VRE. And if we go into a detail on patient degree ratio a bit more in explicit, you can see if we start, for instance, here, we have these infected edges, which are these dotted lines. And then this room here, for instance, has a hotspot score of 0.666. And you have an employee here that has a hotspot score of 0.5. That is what you can calculate from this. And then we can look at basically a ranking of these hotspot scores and look for targets that we want to screen. We also looked into another metric, which is basically the classical node betweenness centrality. This basically tells you how many ways from one patient to the other go through you. So in this situation, from patient 1 to patient 3, for instance, there's just one way, and this is going through the room. And as such, there is obviously just one. This gets a very high chance of having been contaminated. If you go, for instance, from patient 1 to patient 2, this has a direct connection, but this also has an indirect connection via the room and the employee. And so this also provides some evidence about how VRE could be distributed. This metric here is more about something we would call a super spreader, because this tells you basically who is within the way of such a VRE contamination, and as such has a high chance of being contaminated on the way to transmitting it to another patient. Exactly, and then we also looked into eigenvector centrality, which I already explained to you more or less. This is just, again, the same thing. We assign the summed adjacency values to other nodes based on the adjacent nodes. So we start with a certain random assignment of weights for each node, and then we just distribute them along the edges until there is a certain point of stability, and then we can basically see who would have gotten the transmission, the transmitted disease. From this, as I said, we can basically build these hotspot lists from centralities, and here you can see what this looks like for a degree ratio. You can see that there are interestingly a lot of employees and a lot of rooms in this graph, in this hotspot list, which actually means exactly what we could have suspected, which is that employees and rooms actually connect the patients, and it's not usually we usually don't have data about patient-patient interactions. So therefore, this patient degree ratio tells us that a lot of employees and rooms are contaminated. Further down in the list, there are actually also a lot of patients. And in our situation, our screening targets were mainly the patients, because that is something that we can do in our general treatment, whereas dealing with contaminated employees is mostly the more or less the hardest thing, because you have some issues with the classical doctoral oath that tells people that they actually already do the best practice that they could. And then it's pretty hard to tell them, like, you have to wash your hands about double time, because otherwise you might be somebody that contaminates other people. But that's a completely different topic. But that's a thing that is also part of the real world in a hospital. The second approach that we actually were trying to follow is something that we noticed while we were looking at these graph centralities. The thing is, since we are screening only a small portion of the people, we only have data about them and about their VRE status. And because of this, we actually have to drop away a lot of patients that are rather irrelevant for us, except for their interactions that they provide us. but we actually have a lot of data about them, which is, for instance, their diagnosis. So we could actually also model the chance of them getting VRE, because there is actually there is prior research on this, who actually is contaminated more or most. And this data would be highly influential on whether such a transmission actually takes place when people interact. And therefore, we looked into another approach, which is based on graph neural networks. This is a neural network type that can actually work with these graphs, and also allows to add edge and node attributes. In our case, this would be an edge attribute such as the time of the interaction, or a node attribute in this situation, such as patient's age or the diagnosis. You name it. There are a lot of possibilities. And what we are currently looking into is the possibility to use this in order to not only classify patients, but also generate explanations. Because that is one of the major issues within medicine. You usually don't just tell people they have cancer. Usually you tell them why they have cancer and what evidence you have for it. And the same thing happens in this situation. You cannot just tell people, well, screen this person because this black box said so. You have to provide at least some evidence. And it has to be a bit more than just providing some kind of metric, like in the past it has been right all the time. Just because an oracle can do that, at some point, maybe you don't believe it's happening in your situation as well. And therefore, in this, we had this convenient situation that graph neural networks actually can also provide these explanations, saying which parts of the network, which part of the graph they actually added a lot of weight to. So if you look at the picture in the right, you can see that half of the graph was actually not relevant for the prediction, but only some subtype of interaction, and also not all node features were important for this classification. And this is something that we are currently looking into in order to find out whether we can do better than what we did with the graph centralities. And hopefully we can also turn this into something that users actually can use, because how would we make users interact with this? It's probably with this hotspot list, because they are very used to that one, just to look at who has to be screened most urgently. And then it would be possible to actually click on some of the patients on the hotspot list and then just ask, why is this person actually on this hotspot list? And then this explanation can be given, telling basically, you can see here is a certain patient that is positive, and this this chain of interactions could give us the high probability that this other patient is also positive, and therefore you have to find out about this. And hopefully we can also use this data in order to improve the model in the future, because then it can actually add some of its own screening policy to it, and we know more about this just than this proximity-based screening. And well, then the next thing that we also are looking into how to deal with this is usually that people want to look at the situation themselves. As in this previous situation with the hotspot list, they would also want to know how these interactions took place across the whole hospital. And therefore we found out, well, a good visualization is worth 1,000 insights. And we started to think about how we could do this, just to make an interaction that a visualization that somehow helps people to understand the situation. It must be interactive in some sense, because they want to be able to do some kind of data mining. They want to find out, again, their way to their patients. And usually when people are able to track down the data themselves, they are, again, also a lot more believing into their final results, and then they are also putting them onto the screening list. So we can actually help these people to dig into this data a lot more efficiently, and finally also help them to find better screening targets. For this, we used a library that is called holoviz. It's a Python library that can do a lot of crazy things. it is really far-reaching into all different kinds of plots. You can see here different types of plots that they provide as examples. There are plots that are on geographic data. There are plots that are graph network data. And then you can also see that there is more like convenient data. You can add a lot of sliders to it, and that was exactly the thing that we started out to produce a proof of concept, because this is certainly one way that we want to go. We want to build very small working proof of concepts, and then we want to iterate with users in order to find the best approach that matches their typical strategy. And so I'm giving you here some picture of the proof of concept, which is basically showing us this graph that we were talking about before on the actual geographic map. What we can do here for now is pretty primitive, but it helps us to already look into some data, which is that we have a patient ID selector. So if we know the patient's ID, we can click on some of the patients that we want to show. And then we can also set below in this VRE screenings bar, we can select a certain time range, which we are interested in. And if we do this, we can actually look into a lot of different subgraphs, such as this one here, where you can see that there is, for instance, a patient that is here in green. I'm not sure if you can see my mouse. It's somewhere in the top right, which interacted with the Frauenklinik, and I know about that the line would somewhere end up at the other Frauenhospital. So you can see that there's a patient that's somewhere in between there. And if we dig a bit more into this, we can actually find a proper subgraph that helps. When we interacted with our customers, the Spitalhygiene, we were more interested in what they are looking into. And so we actually came up with some more ideas. One of them is basically that we are not showing these kind of interaction graphs, but we are showing them some kind of something that looks similar to a subway map, meaning that we can see how a patient travels through our hospital via its own specific subway route. And then we can see where people meet, and meeting points could, for instance, be the rooms, but also the doctors and the devices. And therefore, we could then say where they meet at the same time is basically the time where we are interested in a contamination situation. What we want to do in the future, there are a lot of more interesting ideas. For instance, one of them is we want to implement a lot of the building data that we have. It's unfortunately also pretty messy because it is somewhere between the different data sources, which is one of them. Within the movement data of the patients, and on the other hand, we have data from the infrastructure department, and this is something definitely a challenge that we are going to have to deal with. But in the future, we hope that we get something like what, for instance, ETH made, as well as EPFL. They made their own campus map, also directly available on Google, where you can zoom into the buildings, and then you can see the different locations. And this would also help us to show the whole interactions, even in a more fine-grained detail, telling people where they were and where doctors have been. And we could even try to model the interactions between doctors on the ward, for instance, which is already one of the issues that we actually have, that we don't have any idea where people passed by and where they were together. For instance, situations like elevators where people travel up and down. This could also be a super spreader that we don't know of. This would then lead in the end to something that we could call an infection risk heat map, helping us to track down these hotspots on a geographical situations, meaning we could even provide information to the infrastructure team telling them to, for instance, heat up the room a bit more, or add these UV disinfection lights, or something which is, for instance, also the ventilation, which can be adjusted. So there are a lot of applications to this that have far outreaching effects on how the daily business of a hospital could happen. Finally, we could also do something like hospital internal contact tracing, as people already know from COVID, where we can actually tell who contaminated whom. We are not yet so sure what to do with these results, because then again, there is a political issue of how to communicate this to different people. But certainly there is this kind of data available in order to do this. And we hope to at least try this in the future and see how far we can go with the results. So yeah, that is basically the end of my presentation, and I'm happy that I could present here. And now, please, I am a data scientist at Insel University Hospital. Ask me anything.